We'll unplug that now. Okay, so any questions over homework? What? 61 in 6.2, right? 61. Okay, so number 61. This is page 419. Whoa. No clickers. I think I've retired them for the year. You're given a function 2 over 3 plus x. And you're asked to find, okay, in this problem, the function is 1-to-1. So they're telling you it's 1-to-1, so you know it has an inverse, right? Find its inverse and check your answer. So was the problem in finding the inverse? Was that the question? Like, okay. So what are the steps for finding the inverse? Replace f of x with y. Then, after you do that, switch x and y. So replace y with 3x. Yes, thank you. Replace that y with x. Replace the x over here with y. And then solve for y. And this was like the one I gave you in class, where you have to actually get this thing, the y, out of the denominator. So you multiply both sides of the equation by 3 plus y, by the LCD on both sides. So I'm going to multiply the left side by 3 plus y. I'm going to multiply the right side by 3 plus y. And what happens on the right side? The right side, these just cancel. And that's the whole reason we did it, is so it would go away. And then on the left side, what is it that we had to do to get this y eventually by itself? Multiply, distribute that x through. So we'll get something like 3x plus xy, or you could say yx, doesn't matter, equals just 2. That's the only thing left on the right side. And we're supposed to be solving for y. So let's get this y by itself, right? So let's, how do we get this y by itself? Get the 3x first off this side. Okay, so move it to the other side, which means subtract it from both sides. That all right? And then divide by x. Divide both sides by x. That's what I think the inverse is. So I'm going to call it f inverse. And then I would go about checking it. Any questions on that part, though? We're all good? Okay, let me do the checking over here. So to check this, what I need to do is I need to show that f of f inverse of x equals x. And after I'm done with that, I need to show that f inverse of f of x also equals x. So there were 2 things I needed to show, right? I'll label them 1 and 2. So let's start with 1 and see if we can show that f of f inverse of x equals x. So these 2 things, you must show this is true. All right, so let's start. F of f inverse of x, by its definition, means you start with f on the outside, and inside you place the inverse function. Now let's replace that inverse function inside with what we just determined we thought it was, which was what? 2 minus 3x over x. So 2 minus 3x over x. And now we're going to take this expression and we are going to plug it into the f function. So we're going to go up to the f function, which is up here, 2 over 3 plus x. We're going to replace that x with all of this. and see what we get. So it was 2 over 3 plus x, but x is now 2 minus 3x over x. Somehow, we need to show that that equals x. So we need to get these two together, these two fractions. So I look at that 3 as really being a 3 over 1, right? And now I say I need a common denominator between these two, so I multiply top and bottom here by x. So x up here, x down here. That makes sense? And now, since they have the same denominator, I should be able to add them together. So let's see. 2 over, I'll write out the line one more time. I have 3x over x plus 2 minus 3x over x. So now these two can come together. So I'm going to take 3x. I'm going to add 2 and take away 3x. So 2 over 3x plus 2 minus 3x all over x. Right? These cancel, 3x and negative 3x. So that leaves me 2 over what? 2 over x. How do I do that? Maybe this will help. Yeah, you flip it. How about if we look at the numerator as 2 over 1? I'm talking about this one right here. This 2 on top, that's 2 over 1, isn't it? Over 2 over x. And that way you can kind of see it is a fraction over a fraction. And then flip that second one up. So 2 over 1 times x over 2. Right? So I'm taking this one, I'm bringing it up, which means I'm flipping it. And then you can see the cancellation. These 2's go away, and you're left with just x, and that is what I wanted. You see that? Any questions? Now, we would be halfway done as far as checking, right? We have to check the other way. Would y'all like me to check the other way? Yeah? Yeah? Okay, so now, on the next page, I need to show that f inverse of f of x equals x. So let's see what this is. This means f inverse is going to wait. Inside of it goes f of x. That means f inverse is going to be out here waiting for f of x, which was 2 over 3 plus x. So now what I'm going to do is I'm going to take this expression, 2 over 3 plus x, I'm going to plug it into the inverse function, which we got back here. This was our inverse, right? I'm going to replace this x and this x with that 2 over 3 plus x. So this is going to be pretty ugly, isn't it? Okay, so this turns into, what is it? 2 minus 3x. So it's going to be 2 minus 3 times, but not x, all of this, right? So I'm going to say times all of that, 2 over 3 plus x. All of that over x, which for us is 2 over 3 plus x. So I'm highlighting, I'll just kind of circle them. Those were the x's, right, in the original inverse function, right? That was like this and this. I replaced those two things with this, and it's pretty ugly. You okay? All right, first thing I'm going to do is put these two together, which means that's like a 3 over 1, and it's multiplication, right? 3 times 2 is 6. So I'll start with that. 2 minus 6 over 3 plus x over 2 over 3 plus x. Now let's just stick to what we've been doing. We've been getting common denominators when possible here. Can I put these two together with common? Yep. So I need to introduce, what, 3 plus x next to the 2, and underneath it, 3 plus x. Do y'all follow that? Okay, let me write the next line. 6 plus 2x over the common denominator, 3 plus x, minus 6 over 3 plus x over 2 over 3 plus x. That's just distributing that 2 through here, right? And now we can put these two together. The 6's, I think, are going to go away. 6 plus 2x, then I'm going to take away 6 all over the common denominator, all over 2 over 3 plus x. Yes, the 6's are gone. Flip it. So, okay, so let me flip it. I'm going to do 2x over this, right? And then the bottom one, I'm going to flip up. So the 3 plus x, sorry, goes on top. And then the what goes on the bottom? 2. You have these two factors cancel because they're exactly the same, aren't they? Which leaves you 2x over 2, which is just x. So we have found the inverse function. We found it algebraically, then we verified it was the inverse. All right, good. So today, we're going to move on to a new topic, all right, new section. 6.3, exponential functions. What's that? You're okay? All right, so I would like to try, if possible, here to do a quick review of the things that we've looked at. Okay, this is a line, isn't it? That's a line. We studied lines. You can have a line that looks like that, right? Equation of a line, y equals mx plus b, right? Then we studied these. That doesn't work very good, right? Yeah, parabola. God, come on. This is like a parabola right here, x squared, well, 0.3. Let me scale this thing out. There we go. Okay, so here it is. X squared plus 4x minus 21. It's a parabola. If I asked you to graph that, you would graph it, right? There's a bunch of steps. Then after that, we went on to like, okay, what if you have like a third degree polynomial? To do this, we figured out where our x-intercepts were, and then we did that whole bouncing, crossing thing, right? Remember that? So that was polynomial functions, lines, parabolas, and then these weird roller coaster looking things. After we investigated those, we moved on to rational functions. Whoa, God. Remember these? Okay, you had like horizontal asymptotes, vertical asymptotes, right? You would have to do all these test points and then figure out if it's above or below, and then what happens is your function's headed towards this, it's forced down, all that stuff, right? So when you look at the big picture, we've looked at lines, parabolas, polynomials, rational functions. We've looked at 4 different types of functions. And now what we're going to study is exponential functions. And then the last one that we'll do is logarithmic functions. So we're only down to the last 2 types. Okay? And then when you take pre-cal, you introduce a whole new set of functions called the trigonometric functions. And there you get the sine, cosine, tangent, cotangent, cosecant, and secant functions. There's 6 of them. And you need to know what they look like and how they behave and all this stuff. So we've got 6 in this class that we really want to understand, 6 in pre-cal. All right? So our last function is called an exponential function. And what I'm going to do is I'm going to try and motivate the idea of where they come from with an example. All right. So I'm going to call this the, I'll say 6.3. I'll try and make my notes somewhat organized today. I'm going to call this the folding paper example. I need someone who is willing to sacrifice a sheet of paper for me, and you won't get it back. There we go. Thank you, thank you, thank you. We've got it. Okay. So now I can't really do this very well. You know, the recording of this isn't going to make a whole lot of sense because they can't see it, but I'll do my best. We start out with a regular sheet of paper. All right. Right now, I have not folded this sheet of paper at all. All right. I have not folded it. How many rectangles do you see? One. So on the side here, I'm going to write down like a table the number of folds, and then over here the number of rectangles. Yeah, we're not going to do that. Oh, by the way, I should also, before we get too much further into this, the lines that we studied, lines are good at, linear functions are good at representing things like, let's say, how many of you have a job where you work hourly? You get paid hourly. Anyone here? Okay, so your hourly wage is a linear function. You work 0 hours, you make $0. Let's say you make 20 bucks an hour, just say. You work 1 hour, right? That's 20 bucks. You work 2 hours, that's 40. You work 3 hours, that's 60, right? That's a linear function. It looks something like this. 0, 1 hour, you're 20, right? 2 hours, you're at 40. So it looks like that's a line, right? So lines are good at representing certain things that are happening, right? Wages might be one. Parabolas, quadratic functions that we studied, I gave you a few examples of those, but one of them was, all objects on Earth fall, if you shoot them through the air, are going to go in a parabolic path, right? Did I give you the example of like a satellite dish? Whatever. So, I mean, parabolas are all over the place. It's good to investigate those. Polynomial functions are also good. I didn't give you a bunch of examples with that, but there are a lot of functions that can be modeled with a polynomial, all right? Rational functions. Did we talk about, yes, I remember talking about this horizontal asymptote, and how with a rational function you might have a horizontal asymptote and your function is getting closer and closer to it without actually ever getting there. We talked about, like, I tell you about that quote that I like. I didn't tell you about the quote I like in that movie Fight Club. Y'all ever seen Fight Club? Here's a quote where he says, he works for an insurance company, and he's talking about his job, and one of the things he says is on a long enough timeline, the survival rate for everything drops to 0. So like if this is time, and this is like whether or not you're alive or not, okay, let's say, the longer time goes on, the less chance you're alive, basically. I mean, just in general, just talking about living things. On a long enough timeline, the survival rate for everything drops to 0. So rational functions are good at modeling things like that where they drop to 0, things are dropping to 0. Another example, without getting too morbid, would be like a light bulb, right? What's the probability? If I just put this fresh light bulb in, it was just checked in the factory, I put it in, I turn on the light, pretty good chance it's going to work. Okay, come back a week later, do it again, pretty good chance it's going to work. Come back in a year, do it again. It's probably work, but it's going to drop off, right? What if I come back in 100 years? Guaranteed it's not going to work? Not guaranteed. Not guaranteed, right? Very small probability, maybe. Come back in 1,000 years. Is it going to work? You know what I'm saying? But you can't say 0, right? You can't say 0. You can't say it would have a 0 probability, because if you still have power going to it and it's connected, then there's the chance that it'll work. So rational functions are really good at modeling behaviors like that, where you have like a value you're going towards, never really getting to it, but getting closer and closer. See, parabolas, you can't do that. Lines, you can't do that. So with that said, the function we're looking at now, this exponential function, is good at modeling certain things also, all right? So no folds, 0 folds, back to this. 0 folds, everyone said you saw 1 rectangle. So if I fold it 1 time, right, and I open this thing back up, and we look along where that crease is as being a separation now, I've created 2 distinct rectangles. Do you agree? So if I fold it 1 time, I get 2 rectangles. So what happens if I take it, fold it back on that one, fold it again now, a second time? I'm going to have 4 rectangles when I open this up. Okay? So fold it, open it up, I have 4 rectangles. 2 folds, 4 rectangles. What happens next? Fold it again 3 times now. That's what I'm asking you. 8, 6. So here it goes. I did 3 folds. So I have 4 across the top and 2 down, so 4 times 2 is 8. So 3 folds gave me 8. And if I fold it one more time, 16 I'm hearing. So what's happening every time I fold it? It's doubling, right? So I have 4 across the top, 4 down the side. So 4 folds gives me 16. What about 5? What do you think? 32. Well, let's see. How about if I did 10 folds? Okay, so 1, 2, 3, 4, 5, 6. That's it, 6. Well, I don't even know if it's a strength thing. I'm running out of paper to fold, 7. No, wait, I was still on 6. I can't do it. I can't get to what 10 is. But could we use the table to make a conjecture as to what it would be? Now, how would you do it? You could just keep going. You could tell me what 6 is by doubling it. Then you could tell me what 7 is by doubling that. What 8 is by doubling that, right? And keep on, and then eventually get to 10. Do you all agree? Yes? It's got to be a better way. There's got to be a better way, because what if I wanted to know, if I could fold it 60 times, what do I get? You wouldn't want to create the table all the way out to 60. So I wonder if there is a function, is there a function that actually you plug into it this number and it spits out this number? Right? Where I would plug in 0 and get 1. I plug in 1, I get 2. I plug in 2, I get 4. I plug in 3, I get 8. I plug in 4, I get 16. 5 and 32. So you're thinking x squared maybe? Maybe, I don't know. I mean, 2 squared is 4. I agree with that, but 1 squared is not 2. And 3 squared is not 8. So it can't be x squared, right? So let me try and help you see this. Do you agree that this, I'll start with the 2, that 2 is the same as 2 to the first power, and that 4 is 2 squared, and 8 is 2 times 2 times 2, so 2 cubed, and 16 is 2 to the 4th, and then this would be 2 to the 5th. Do you see that the power on the 2 is actually the number of folds I have? Yes? And do you see it even works for the first one? 2 to the 0 is 1. Anything to the 0 is 1. So it works for this one also. So that means my function over here, if I define it, it's no longer a question mark. If I define it to be 2 to the x, then this should create this table. Do y'all see that? Now, yeah, x would be the number of folds. So if I wanted to know how many rectangles I would have if I could fold it 10 times, I would have to do 2 to the 10th power. So if you have your calculators, now would be a good time to get them out. If you don't have them today, start bringing them from here on out. Forgot to tell you all that last time. Today you can use your phone if you have your phone. Two to the 10th power. 1,024. So this would be 1,024. So if I could fold it 10 times, I would have 1,024 rectangles. And I'm doing that by doing 2 to the 10th power. Now 2 to the 60th, you're going to have a problem. Yeah. Yeah, it's a huge number. Yeah, it's got 18 decimal places. So it's something like 11529 21505. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18. There you go. That's the number right there. Close enough. This is approximately the number. It's an astronomically large number. Okay, so look, let's just get our heads around this function and what's different about it. Compare it to what we've studied in the past. Where does the variable appear? In the, what's that thing up there? In the exponent. Why don't we call them exponential functions then? Because the exponent is the variable, right? Let's call them exponential functions. As opposed to, look at that compared to, so versus this function, I'll call it g of x so we don't call the same function, x squared. This is a parabola, right? The variable x is in the base on the bottom. The squared is always squared. The power never changes. The exponent stays the same all the time. Versus this one where the base stays the same all the time, the exponent is the thing that changes. See the difference? Okay, so we already studied those, so we're not here to talk about that today. Okay, everyone understand? All right, I'm just trying to motivate the idea of where these things come from. Let's look at another example. A certain bacteria quadruples. Is that how you spell quadruple? P-E-L? Quadruples? Oh, wait, okay. Quadruples daily. Find a function modeling its growth. All right, so if any of you have taken like a biology class or something, they have that petri dish, like a sterile dish, and then you put something in it and you close it and you come back a couple of days later and you go, holy shit, look at all that stuff in there, right? It's like bacteria growing. There's a certain bacteria that quadruples daily. So every day it quadruples. And I want to get an idea if I can come up with a function that models this sort of growth. So let's take a look at our bacteria. Here he is. Oh, sorry. There she is. That's our little bacteria, right? We put that one little bacteria into a dish. One day later, what do I have? I have 4 of them. I'll still put smiley faces. They're still pretty happy. Happy bacteria. Okay, so that's 1 day later, right? 1 day. 1 day after that, what? Each one of those splits into 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So now you are starting to get crammed in there, right? Now I have 16. What about a day later? Uh-oh. Okay, you're starting to grow pretty fast, right? So let's try and do a table to see if we can come up with some sort of relationship. How about this is day, and this is number of bacteria. On day 0, how many bacteria were in there? 1. 1 day later, how many were there? Day after that, 16. And the day after that, we didn't do it, but how many would there be? 64. So each one of these would have 4, right? Is that right? 64. Does anybody see that this is an exponential function? This is 4 to the first power, 4 squared, 4 cubed, right? 4 times 4, 16, times 4 again is 64. And then the first one was 4 to the 0. So the fact that it said quadruple led us to understand that it's going to be 4 to the x would be our function. So f of x equals 4 raised to the x would be a good model for this growth. Where x is what? Days, right? Number of days that have gone by. 0 means no time's passed you had that first bacteria in there. 1 day later, you have 4. Understand? Then if you had a bacteria that tripled every day, it would change to what? So it tripled instead of quadrupled. 3 to the x, right? No logs yet. Okay. One more example, and then we're going to get to a definition. So I'm going to start with a sheet of paper, this same one. Oh, wait, I folded it up. Wait, you know, I don't need another sacrificial one. I didn't even realize I had one right here. Okay, I have a sheet of paper. And let's just say that it's, for the sake of making this simple, let's just say it's 1 foot long, all right? I know it's not 1 foot long, but let's just say it is, right? What I'm going to do is I'm going to come in here with a very precise instrument, and I'm going to cut it right in half. Here's my precise instrument. That's pretty good. I cut it in half, right? How long is it now? Half of a foot, or 6 inches, right? But let's say half a foot, right? So I had no cuts, right? Here comes a table. Cuts are here. Length is here. 0 cuts, it was 1 foot. 1 cut, cut it in half. Take that piece, throw it away. How long's what's left? Half a foot. So 1 cut, half a foot. If I cut that in half, how long is this? A quarter? Half of a half, right? Half of a half, which would be 1/4. Cut that in half. Half of a half of a half, so 1/8. Oh. There we go. Cut that in half. So I'm going halfway, throwing it away, halfway, throwing it away, halfway, throwing it away. So this next one, 4, was 1/16. So what are the properties of this? This is 1/2, right? This is 1/2 squared. It's 1/2 times 1/2, isn't it? 1/2 times a half, you multiply straight across, 1s, 2s. This one would be 1/2 cubed. This one would be 1/2 to the 4th. Do you see it? And then, of course, the first one was just 1/2 to the 0 power, right? 1/2 to the 0. So what should be the function that is dictating what's happening here? 1/2 to the x. So in the previous two examples, we had as that base, we had 2, right? That was the folding paper problem. Then the bacteria, the base was 4. And now I give an example where the base is 1/2. And what you can see is that there's a difference between what's happening. When we had the bacteria, as we moved down, this number started getting very big, didn't it? And same with the folding paper. This number got really big. But when we put 1/2 in there, what's happening? This number is getting smaller, smaller, and smaller, and smaller. However, is it ever going to be 0? No. I mean, I can keep going half, and half, and half, and half. Theoretically, I can always take half of a number, right? And get a number that's not 0. So I should be able to keep doing this, and it should get smaller and smaller and smaller. Make sense? In fact, if I go out to 10 cuts, I get 1 over 1,024. Type that into your calculator. What's 1 over 1,024? Approximately as a decimal, what do you get? Point what? 0.00097? 65 something, 65, whatever. Okay. So this number is really small, right? 0.0009. But it's not 0, right? It's a little bit bigger than 0. And if I went out to 60, it'd be 1 over that huge number we had, right? 1 divided by that huge number, which is still a very small, 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 small number, but it's not 0. So I hope that this gives you some idea of how these things behave. Yeah, let's now get to a precise or more precise definition of what an exponential function is. Where am I? That should have been 6.33, that halving paper. The next one will be 6.34. Exponential functions. If you have a function that looks like this, I want to use the exact notation of the book. This is what an exponential function looks like. All right? Capital C is a number. Capital C is not 0, because if it was 0, the whole thing would just be 0. Little a is the base of the exponential function. Little a must be greater than 0. So when you have the base, remember I gave you, what, 3 examples? 2 was the base for the folding paper, 4 was the bacteria, and the cutting the paper was a half, right? In all the cases, a must be a positive number. Exponential functions are not defined when that is a negative number, so we just don't even look at that. Also, a cannot be 1. Because if a is 1, what's 1 raised to any power? What's 1 squared? Right? 1 cubed, 1. So if you raise 1 to any power, you just get 1, and it doesn't behave like an exponential function. So we just can't have a being 1. It's okay to be 2, it's okay to be 4, it's okay to be a half. Has to be positive, can't be 1. You okay with that? Okay. The number C is called the growth factor. Oh, sorry, A is the growth factor. A, I was like, that didn't make sense, is called the growth factor. C is called the initial value. Now let's see why it's called the initial value. The growth factor, I hope you're okay with that. When we had 2, when A was 2, it grew, right? When A was 4, it grew even faster, didn't it? So the A value actually determines how fast this thing grows. C is called the initial value. Initial, when you say initial, do you think like beginning, right? The beginning value? So when we say beginning value, let's just plug 0 into this right now. What is f of 0? I'll put this right underneath this. Why is it the initial value? What's f of 0? It's c times a raised to the 0, right? Replacing this x with 0. What is a to the 0? What's any number to the 0? 1, right? So it's c times 1, which is c. So that's why they call it the initial value. Whatever the number is out in front here, whatever that is what you get when you plug in 0. So it's always your starting value. Now, for all the examples I gave you, our starting value was 1 because I chose c to be 1 when I was giving you the examples. Okay, so all exponential functions look like this. Now, a couple of other things. How do you say this? This right here is the base A exponential function. You can also say the exponential function with base A. Questions? Yep. With base A. That's fine also. All right, I'm going to proceed. If someone wrote f of x is 2 to the x, right, like the folding paper, you would say, oh, that's a base 2 exponential function. Or you could say that's an exponential function with base 2. Graphs of exponential functions. What do these things look like? Well, it's going to depend, all right? Let's look at a little animation thing I have here. This is the graph right here. This is the graph of, look at my C value is 1, capital C is 1, little a is 2, and then I have the x. What did we get when we had 2 to the x? What did we get when we plugged in 0? 1, right? So look at this graph. When I plug in 0, it spits out 1. Do y'all see this is 1, 2, 3, 4, 5? You'll see that? So when I plug in 0, I get 1. When we plugged in 1, what did we get? 2. 1, 2. I'm right there. When we plugged in 2, what did we get? 1, 2, 3, 4. That's right here. Do y'all agree? When I plugged in 3, I got 8. And then when I plugged in 4, I'm 16. I'm off the charts, right? I'm off the chart here. But do you see that it would keep going up, and it starts going up very quickly, doesn't it? What we did not do is talk about what happens if you try and plug a negative number in. We didn't talk about that yet, did we? So I want us to entertain the idea of plugging in a negative value. And what we're going to see is that we're going to get this behavior. Let's confirm that, okay? Let's confirm that that happens. So as an example, let's look at 2 to the x again. It's a specific example of an exponential function. When we made our t-table, we would say x is here and 2 to the x is here. We had plugged in 0, 1. 1 gave us 2. 2 gave us 4. 3 gave us 8. 4 gave us 16. Agreed? But now let's plug some negatives in. So I'll do the negatives in red. Although you can't really tell it's red, so I'll do them in green. But you can't really tell it's green, so I'm going to do them in blue. You can't even tell it's blue. All right, let's try -1, then -2, and let's just do -3. We'll just do those 3. All right, so what would happen if you plug in -1? Let's see. That's 2 raised to the -1, isn't it? What does it mean to raise something to a negative power? So you have to remember some properties of exponents. I'll write down the property I'm going to use right now. If you have something raised to a negative value, that's the same as 1 over that raised to a positive value. You may remember it as if you have a negative, you can drop it down, something like that. That's what I'm going to do here. I'm going to rewrite this 2 to the -1 as 1 over 2 to the +1, but what's 2 to the +1? 2, so that's just 1/2, isn't it? 1/2. 2 to the -1 is 1/2. I've actually done this before. My wife always gets pissed off at me when I do it, but I'll go to like H-E-B meat market and I'll be like, I'll take some of that ham, and how much do you want? And I'll be like, 2 to the -1 pounds, please. They're like, what? What? 2 to the -1. Half a pound, right? Come on. Huh? That look that I was just giving you? Like, what? I said, never mind, just half pound. So 2 to the -1 is 1/2, right? 2 to the -2? That's going to be 1 over 2 squared, which is 1/4. Or a quarter, isn't it? Go to McDonald's and order a 2 to the -2 pounder. Let's see what they say. All right, 2 to the -3 would be 1/8. Okay? So what's happening as we're plugging in negative values, right, our graph going out the left side, these values 1/2, 1/4, 1/8, they're getting smaller and smaller and smaller. And I believe that matches up with this, right? If I plugged in 1, what did we have? 1/2. When I plugged in 2, 1/4. When I plugged in 3, 1/8. 4, 1/16. Sorry, -1, -2, -3, -4. So they're getting smaller. But we said they never get to 0, do they? So we have, what do you call this when it gets closer without actually getting there? We call that a asymptote, a horizontal asymptote. We actually have a horizontal asymptote in this graph. But it doesn't go out both ends. It only goes out one end. Right? Okay, so with this idea, I'm just going to sketch it real quick just so you'll have it. With this idea, 2 to the x looks like this. We have a horizontal asymptote right here, don't we? In fact, it's the x-axis, which is the line y equals 0. As long as we don't shift this thing around. Do you remember transformations? Do you remember if I give you a parabola and I say add 2, it moves the whole thing up 2? Same thing will apply here. But first we get a basic idea, like we're just basically going to add this function to our toolbox, and then we can shift it, flip it, reflect it, do all those things. Okay, now this right here, right, this function is taking off, right? It's going up to infinity, taking off to infinity, isn't it? Up to positive infinity on the right side. It's almost like the polynomials we had left-right behavior. The right behavior of this function is that it's going up forever, yes? And it's going up very fast. The bigger the number is, the bigger that base is, the faster it goes. So you've heard of this before. If you just watch the news, you know, I guarantee you if you watch the news for a day or two, you'll hear them say exponential at least one time because they love using it. They're like, you know, crime rate in South Texas is growing exponentially, right? They love that shit. They love that word. It's just a way of telling you it's growing fast, right? Exponential is very fast growth. Yes? Okay, that's what we mean, exponential growth. And in this case, it would be growth, wouldn't it? There is going to be another variation, watch, we're going to do it here in a second, where you don't actually have exponential growth, you have what's called exponential decay, where instead of it growing very fast, it's going away very fast. That was me tearing the paper. It was going away quickly. Okay, we good? Is it clear that we can plug negative numbers into an exponential function? Okay, now let's contrast that with this example. F of x equals 1/2. I was doing imitations of news broadcasters. That's what you missed. It was good stuff. So let me show you the picture of this first. I'm going to change my base to 1/2. There it is. So C is still 1, but my base is 0.5 or 1/2. What happened to the graph? Now let me go back and show you. This is where it came from. And this is what happens when I change it to 0.5. There's something very critical happening right at, here's 1, right? When it's 1, it's a flat line. And I said the base can't be 1, right? Because if you do 1, you get a flat line, that's not an exponential function. You don't have exponential growth or anything. So if the base is, look, bigger than 1, we get exponential growth, don't we? But if the base is smaller than 1, but still a positive number, then the graph flips over and you get the opposite, right? As you move to the left, it's going up. As you move to the right, it's going towards the horizontal asymptote. Yes. That would be decay. It's like we would read it in a book. You know, when you read a book, you read left to right. When I'm looking at this and I'm going from left to right, it is going down. So it's decaying, as opposed to when the base is this. Now when I move from left to right, I'm growing exponentially. Exponential growth. Okay. So from this, let's create a quick table. Now you're going to have to be able to graph these by hand. All right? So I will expect you to do a table. Yes? And I always expect you to use the same values. That way we all get the same results. I want you to grab a couple of negative numbers, a couple of positive numbers. Here's the ones I want. -3, -2, -1, 0, 1, 2, 3. That's usually enough for us to get an idea of what's happening. So do you think I don't know you're texting over there? Do you think I don't know? I'm just curious. No? I do know. I wonder if people actually think I don't know. Like if it's somehow you think you're that good that you no? Okay. I'm just wondering. One of these days you won't even have to like use your fingers, right? You'll just be sitting there thinking. Texting. I thought about this about 10 years ago. When you think about what mental telepathy is, right? Is communicating with someone without like verbalizing, right? Right? I mean, we will get to that day, right? Where if I want to communicate with someone, it'll probably be like a chip or something that I have, and it'll just be like, yeah, I know, right? And I just texted my friend. What's that? Where's what? Who does? It's a great idea. I think when you're born, you should just like put it right in the base of your, like in the base of your skull, so it can't be removed easily. You know, like. I'm kidding. Come on. Exactly. I mean, this is where we have to get some. Well, you would eliminate a lot of issues with crime, right? You eliminate. Oh, were you there? Was it you? Well, let's just see where you were. Yes, you were. It's Big Brother, but okay. Anyways, let's get back to exponential functions. See, it's distracting. Texting is distracting, even in a classroom. All right, so look, what does it mean to raise 1/2 to the -3? So again, let me draw back on properties of exponents. There was a property of exponents you may or may not recall that if you have a fraction to a negative power, you can flip the fraction and it becomes a positive power. So what's on top goes to the bottom, what's on the bottom goes to the top, but the power changes to positive. So this turns into y over x to the n. Just remember that property. So if I have 1/2 to -3, I can flip the fraction and make it 2 over 1. But now to the +3, which is 2 to the 3rd, which is 8. Isn't it? Then take 1/2 to the -2, and what would you get? 2 to the 2, which is 4. The next one would be just 2. And then what's anything to the 0? 1. Well, I say anything to the 0. I have not talked about what 0 to the 0 is, but I've told you, I think, before that that's what you do in calculus. You talk about that. 0 to the 0. It's not a good thing. All right. It's not imaginary, no. It's just not defined. Okay, so what about 1/2 to the +1? That's just a half. And then 1/2 to the +2 is 1/2 times a half, which is a 4th. And then 1/2 to the 3rd, which is an 1/8. My friend just posted something on Twitter. It's hilarious. I mean, can you imagine that society? Like, I mean, you're sitting there the whole time. You're just like in your own world, just like, check out that video. You know, you're sitting there thinking. I mean, what is reality anymore, right? That's where we're headed, right? No, I mean, imagine that, right? I mean, how could you ever pay attention to anything? No, you just won't have to. We won't even. It'll be like Matrix. You'll just be hooked up to power. That's it. You'll just need power, right? And then you'll be in some artificial reality. That's right, man. This could be good stuff. All right, look, I'm sorry, I'm really sidetracked today. I'm happy because I'm in a good mood. Yesterday was terrible, terrible day. I had Cal 1 class, online class, 1 student passed the midterm. 1 student. Yeah, I was very depressed yesterday. Online. I don't know. I've never had that happen. Okay, so look, let's try and get an idea of the graph. I mean, we already talked about what it was, right? We already know it looks like this. Let's just verify real quick that that's what happens. I plugged in 3 values to the left and 3 values to the right. Let's just plot these like ordered pairs. When you plugged in -3, we got what? +8. So that means I go to -3, I go up 8, way up here somewhere. I plug in -2, I got what? 4? Somewhere around here. Plugged in -1, I got 2. Plugged in 0, I got 1. And then they started tapering off, 1/2, 1/4. And so we got that picture like this. Notice our horizontal asymptote is still here. It's still the x-axis. And this would be, as we go out this way, right, it's going up to infinity, out the left side. And we also have that this is called decay. Exponential decay. How many of you have studied in chemistry or physics or something like that, something called half-life? I'm not talking about the video game. Half-life, pharmaceutical, half-life, right? You have medication, bone decay, carbon 14 dating, yes? Okay, so half-life is like the best analogy I can think of is like if you ever been camping and y'all did like marshmallows, you have a big old campfire, it's real hot at night, right? You go out there next morning, right, and you're like messing around and it's still hot, right? You start moving stuff around, it's still like coals burning in there. You know, you come back hours later, it's still going. Maybe the next day it's still warm, right? This is the idea of kind of exponential decay. You start off with something, and as time goes on, it goes down, like heat in that fire. Starts out real hot, and then it starts to decay down, right? Now, eventually, with a fire, it does eventually go out. But with things like radioactive material, it never completely goes away. It's like tearing the paper in half, tearing the paper in half. It's always still, some of it is there, all right? So you get these very, very bad radioactive isotopes that are using like nuclear weapons. And what happened is, even though you drop the bomb or whatever it is, years later, it's still there because the half-lives are not like a day or an hour. The half-lives are like 10,000 years. So you start with maybe, I don't know, Chernobyl. I know you're from, are you? That's right. Chernobyl was a city in Russia. Nobody lives there, right? Because they had a nuclear reactor meltdown, and the radiation from what was left there, no one could basically go in there and get it out because you basically died doing it. In fact, people did die doing it because when it melted down, they had to send not rescue crews, but they had to get volunteers to go in there, and they just poured concrete in this big hole because it heated up like almost to the core temperature of the earth, you know, like really hot, and kind of like melted through into the ground. So they just like poured concrete on it. A bunch of the guys that did that died later. They evacuated the city. It was I believe, Chernobyl, the amount of radioactive material that melted down that day, it was 10 pounds. That was it. And it's still radioactive to this day. And that was back in, what, do you remember, 80s, early 80s? I don't know, 30-something years ago. But the half-life is so long that it's not going anywhere, okay? Because, okay, let's go back to our piece of paper, right? If this is going to decay exponentially, then it's going to take a certain amount of time for half of it to go away. Now, depending on what this is, will dictate how long that is. So you have certain things have certain half-lives. Some things decay very quickly, like medication, right? You can have medicine that goes, they say, goes bad within a certain time. It just means it's ineffective. It means within, let's say, within 6 months, half of it is decayed. 6 months later, half of that's decayed. So now this is really 1 year later. Another 6 months, right? Another 6 months. So now imagine that instead of 6 months, that was 6,000 years. 6,000. Did you look it up? 1986, yes, was when they had the Chernobyl meltdown. So we're right around what, 30 years? About 30 years ago. No, it varies. It depends on, the radiation is coming from, I don't know if it was plutonium or uranium. I'm not sure what they were using in there. I'm not sure what it was. Yes? I don't know. You can look it up. We could Google it. But that's the stuff. And it's the thing that makes it radioactive. The thing that is bad about radioactive material is that it's almost like standing in a microwave, right? You stand in a microwave, or you get X-rays, and they always put that lead vest on you or something, right? Well, that's to protect your cells from being damaged by the X-rays. Well, radiation is even worse. And so what happens is it goes in there, it actually messes up your DNA. So it fries your cells, and then your cells stop behaving the way they're supposed to. And so, yeah, it messes you up real bad. So, all right. There was a textbook I used to teach out of that had a great section that talked about Chernobyl and radioactive decay and all this stuff. What I want you to see is that exponential decay is great at modeling things like half-lives. I mean, that's what it's all about, half-life. And exponential growth is also good at modeling things when you want it to grow very quickly. So in summary with this, we have two possibilities, right? We can have growth and decay. So when do they happen? So let's just summarize here. You have two different pictures that we can get. We can get this, or we can get this. This is growth. This is decay. This happens if A is bigger than 1. This happens if A is between 0 and 1. Remember we said that A had to be positive, right? A was the base. Said it had to be positive. That was a given. So if your base is like a fraction 1/2 or even like 0.2 or something like that, you're guaranteed it's going to look like decay. If your base is a number bigger than 1, you're guaranteed the growth. All right? Some other things to point out here. 0, 1, that point actually appears on both graphs, doesn't it? Actually, we should change this. Leave the 1 there, but put above it C, capital C. That's our initial value. All the examples I've given you, it's been 1 because I used 1. But in general, on an exponential growth or exponential function, if your function looks like this, C a to the x, then when you plug in 0, you get C. But it'll be on both pictures, either one. What else do we have? These horizontal asymptotes, right? You should have a horizontal asymptote for an exponential function. One side should go up to infinity, right? One of the sides should go up to infinity. What about the domain? Let's talk domain. What's the domain of an exponential function? Look at the pictures. Everything, right? They go in both directions forever. So your domain is everything. However, what about your range? Can't be below 0. Can't be 0, right? How about 0 to infinity? Just positive numbers. The only thing that comes out, if you go up the y-axis, start looking left and right, you're only going to get function above, you're only going to get graph above 0, right? Unless we shift it. Yeah. Questions? Comments? Yes, unless we move it up or down, okay, which we haven't done yet. Then it's not an exponential function. It's not something we study. No, not really, because the problem you run into is that if you have a negative number, we know that if you square a negative number, it's positive. If you raise it to a third power, right, negative to a third, it's going to be negative. And then what happens if you take a negative number, raise it to like a decimal, a negative decimal? And then what happens is you get a graph that's scattered. It's not continuous. You can't draw it without picking up your pencil. So it's not something we normally study to begin with. All right. We good? All right. Now, I'm looking at the book to see which part of this I want you to focus on. Let's look at two specific exponential functions that are very important to us. Two important exponential functions. This is 6. First one, f of x equals 10 to the x. Now that there is your just standard base 10 exponential function, right? Base 10, because the base is 10. Now why is it that you think that that would be an important exponential function, as opposed to 2 to the x? Why do you think 10 is important? Mm-hmm. Well, they grow. That's it. Our number system is base 10, right? We have a base 10 number system, don't we? Base 10. That comes from 10 fingers probably, right? Right? If we had 8 fingers, we'd probably be base 8. I mean, most likely. So that's just because our number system is base 10. So if you're in a chemistry class, you do like pH scales and things like that, all that's base 10. They're using the base 10 pH scales, and it's base 10 exponential and log functions, which we haven't talked about. But I'll give you a little preview. Guess what a log function is? Guess how it's related to an exponential function? It's the inverse. That's all it is. We have an exponential function. I wonder if there's a function that undoes it. Yes, it's called the log. So that's where we'll go there, but let's first get the exponential down. So there's your base 10 exponential function. And the next important one, and in my opinion, the most important one, is e to the x. Here, the base is e. Now, what is e? E is an irrational number. Like pi. You've heard of pi, right? It's a non-repeating, non-terminating decimal. It's this thing that keeps on, if you write it out, it goes on forever. It doesn't have a pattern to it, just like pi. Now, it is actually, e is approximately 2.718, and it keeps going. It's approximately that. Approximately. That's the thing about an irrational number. You cannot, it's impossible for an irrational number to be a fraction. It's not possible. Now, you can approximate it that way, but you can't. 22 over 7, though, that's the approximation of pi. No, it's approximation. Yes. Yep. Not every number can be represented as a fraction. The irrational numbers cannot be represented as a fraction. What's that? I was wondering how you got pi. Well, pi by definition, pi is exactly the circumference of a circle divided by its diameter. That's the definition of pi. It's impossible for that to ever be a fraction. We can approximate as far as we want. And for all applications, at some point, you're building something, there's a certain tolerance that you'll be happy with. So, okay, so this base E, all right, is what we call the natural base. Base E, the natural base. The natural base. Now, how many of you that have taken some algebra maybe in high school have heard of something called the natural log? The natural log function? It is the inverse of the natural base E function. It is that specific function's inverse. We call it the natural log. Now, the reason why it's called the natural base comes from the fact that as humans, as we kind of developed, if you believe in this, we needed to tackle some problems, like maybe trying to put men on the moon. I don't know, trying to create rockets, whatever it would be. We were trying to advance, right? And as we were advancing, we were saying to ourselves, man, we really would like to have this function. We're looking very hard for a function that behaves a certain way. It needs to do X, Y, Z. It needs to do these things. And we were looking around for, wondering, does it exist? And then we actually found it. And this is the function. This is the function that does what we needed it to do. And not only is it the function that does it, it's the only one. It's unique. And so the question becomes, well, why is it the only one? Well, I don't know. It just naturally is the one. It's the one. All right. So it is the natural exponential function. So this one is used extensively in mathematics, physics, chemistry, everything. All right. Just keep in mind that the base of this is 2.718, approximately. So if I were to ask you to graph both of these, would these be exponential growth or exponential decay? They'd be growth, right? Both of them would be growth because the base on both of these is bigger than 1. So let's try and see if we can do this one. I want to graph this one, e to the x. I'd like to graph it by hand, making a table. X, e to the x. What are the standard numbers we're going to plug in? -3, -2, -1, 0, 1, 2, 3. And over here is going to be my graph. We already know it's going to look like exponential growth, but I want to actually know what the values are. So the first thing I'm going to need to do is I'm going to be able to need to do e to the -3. And I have no idea what e to the -3 is. So I'm going to get my calculator out. And this is why you need to bring your calculators, because on a test, you can't use your phone. You need to be familiar with your calculator and know how to do e to the -3 or anything to any power. So with whatever you have in front of you, try and find your E button. And there's 2 different E buttons on most calculators, so we're going to make sure you got the right one. And try and do e to the -3, and somebody tell me what they get. You should get approximately 0.04978. That's good enough. So, if you have a calculator right now, and you are not getting that, please raise your hand, and I will come help you get it. If it's your phone, I'm not going to really help you. Okay, so this is, every calculator is different. Here's your E button right there, e to the x. Okay, so first thing you have to do is you type in 3, negative. Okay, so this calculator wants you to give it the power first, -3. Now, what do you want to do with that? You want to take shift, you want to take E of that.
Okay.
Got it?
All right.
Anyone else need help with their calculator getting that? 0.0497. Okay, now do e to the -2. Yep, 0.135. And you could say 3. It really doesn't, you know, we're not, you're going to have to graph this number. And that's not going to be very easy for us to do. Like, how are you going to distinguish 0.0497 from 0.15? It's going to be very difficult. So let's just say, standard rule of thumb, let's go 4 decimals for these, okay? 4 decimal places. What's e to the -1? 367. Good enough. E to the 0? 1. Yay. All right. E to the first power. 2.718. 3 decimal places. 4 decimal. 3 or 4. I don't care. All right. E squared. 7.389. E cubed. 20.85 or 86, whatever. The whole reason I'm doing this, I want you to just practice with your calculator. Type, you know, how to do something to a power. And then you plot these points. So when I plot this, look, what's the largest y value I'm going to have? What's the largest y value, not x? The largest y. 20. So I'm going to put out here, like, let's say this is 20, right? Oh, I thought you said 3. Oh, you did? I heard you say 3. Okay, I'm sorry. So at 3, it's 20 point something. So I don't know, it's somewhere around here, give or take. When I plug in 2, I'm at like 7 point something. I'm about there. When I'm at 1, I'm at 2.7. So I don't know, around here. Then I'm at 1, and then it's going to decay down or go to my asymptote. I missed it. I missed it big time. When I miss it, what do? I just make my dots bigger, right? There we go. So if I were looking at this on like a quiz or something like that, I'm looking at your table to make sure your values are right and that your picture looks right. It's impossible for me to do 0.367, 0.135. I mean, it's just, as long as I see that asymptote here, the dotted line, that lets me know it's going down towards it, I'm good. Yeah. Because the table shows that you know what the values are. All right. Questions? 637. Transformations of exponential functions. Transformations of exponential functions. Let me see if I can find your notes. Where was it? Graphing techniques, transformations. Okay, so in your notes from 3.5, graphing techniques, transformations, we had this stuff. Vertical and horizontal shifts. Adding a number moves it up. Subtracting moves it down. Adding a number inside the function next to the x moves it opposite of what you thought, to the left. Subtracting a number inside next to x moves it to the right by that much. Reflections and stretches, all this stuff. Please refer back to these notes because that's what we're about to do. All right? Everything is the same as what we did here, except that your given function, right? Given a function whose graph is known, we know that function now is to be this exponential function. Now we're going to move it up, down, left, right, flip it over, stretch it out. So here's an example. Sketch f of x equals negative 2 to the x plus 1 plus 4. All right, so what is the toolbox function that we're looking at here? What is our base function? Our base function is 2 to the x. Also, be careful. See this negative? Order of operations here. This negative out here is not with the 2. It's by itself outside in front, almost like a negative 1. If I wanted that negative inside with the 2, I would have had to have done this. Then your base would have been negative, and then we wouldn't have been able to do it because we said you can't have negatives. Understand? So when we look at this, we're saying, okay, we know that this looks like 2 to the x. It's just been transformed. Do we know what 2 to the x looks like? Sure. We've already done that one, right? So what you would have to do now is make your table, -3, -2. I'm doing this very quickly because we already did it. 1/8, 1/4, 1/2, 1, 2, 4, 8. Right? That's what 2 to the x looks like. Agreed? Now I could come over here and I could draw it. Again, moving quickly because of time. Let's say that's 2 to the x. That's not my answer, right? Now, tell me what I want to do with this picture. We have to remember, you have to go order. The order has to be correct here. You start here. You have a +1 next to the x. What does +1 right next to the x do? +1 next to the x. So if you plus 1 next to the x, it's going to shift it left by that much, right? If the added number is in there next to the x, it's a left or right shift. So I'm going to move this thing to the left 1. Then you have to do this next. What's a negative sitting in front of the whole thing do? Negative in front of the whole thing, reflecting it over the x-axis. And then up 4. So what I'm going to do is I'm going to take every point that I had, move it to the left 1, flip it over the x-axis, and then move it up 4. So watch me do one point. Let's do the point 1, 2. Wasn't that a point here? Wasn't that a point on this graph? Okay, take this point, move it to the left 1 first. That would take you here, wouldn't it? Now take that point, flip it over the x-axis. Where does it go? To -2 down here. You'll see that? Flipped it over the x-axis. Now, up 4, the whole thing up 4. So I count 1, 2, 3. Where am I? Right back to where I was. That's okay. All right? That's just that one point. Do you all see that? Left 1, reflect x-axis, up 4. Let's do one more point. 2, what was 2? 2 went in, it was 4, right? Move it to the left 1. Flip it over the x-axis. Where is it now? Down here at 2, -4, isn't it? Now move it up 4. Oh, wait, 1. Yes, 1, sorry. 1. That's what you were saying. Bless you. Okay, so it went from 2, 4, moved over to left 1, so now it's 1, 4. Then it flipped over down here. It's 1, -4. Now move the whole point up 4, 1, 2, 3, 4. It puts it on the x-axis, doesn't it? 1, 0. You got to do that for every point. Yeah, that's why I only want those specific points. Now, I'm going to finish drawing it, but tell me about the horizontal asymptote. It moves as well, yes. What happens? When I move the whole graph to the left 1, does it move the horizontal? No, I mean, it moves it to the left 1, but that doesn't change. It's a flat line. Reflecting it over the x-axis, that doesn't move that either. It is the x-axis. But at the end, it's what? Up 4. So this goes up 4. Let's say 4 is right here. So now my horizontal asymptote's up here. Let me do one more point. Let's take, you want to do -3? Okay, this was the point, -3, 1/8. Move it to the right 1 first, or left 1 first, which is here. Flip it over the x-axis, which puts it here. So what is that? -4, -1/8. Do you all see that? Started at -3, 1/8, moved over to -4, 1/8. Now flip it over, it's -4, -1/8, and now move the whole thing up 4. 3 7/8. It's going to be up right above 4. So it's going to be up right here. And what you can kind of see, hopefully, is your final picture like this. Why do you have to? Well, because knowing just the basic exponential function only allows you to deal with just those, right? But in reality, a lot of times they are shifted or flipped over. They're not just always starting right at the origin, always going up. Sometimes you want to move them over. Let's say you had decay, right? Let's say you had exponential decay. Like that. But you didn't want it to start here. You wanted this to be your initial value. You would have to move the whole thing over, right? And then do this instead. So you need to transform it from what it was to something new. Okay. You think you can handle that? It's going to be a little messy, but I would like to know what the transformations are. Only because the graphing calculators, you can just type it in and then it graphs it and kind of defeats the purpose. Yeah, you would write, left 1, flip, x-axis, and then up 4. Is it always what? Like what? I mean, in that order? You're always working from x out. So you start here, right? And then you do this because this is multiplication between these two. Then order of operations, then add. You never do add first before you do the exponents. Yeah, you have to know what the basic function is first. Okay, let me tell you what to look at for your homework. And we're not done with this section. We have more to do here. Page 432. $15, 21 through 24. $33, hold on. 31, 34, 36, 36 through 39. And that's it. Now look, on top of this, I want you to sketch f of x equals 4 to the x and g of x equals 1/4 to the x. Just practicing making that table and doing a table for both of those. On these right here, what they do is they give you a function and they ask you to try and match it to a picture. So they give you the functions and then they want you to match which of these graphs goes with it. So they have the transformations already there. So you're supposed to look and say, oh yeah, that looks like they moved it to the left one, flipped it over, and then you just try and mix and match those. All right, we'll do more on what? Thursday? Have a good day.